today's topic is basically running on ThetaGPU with Nvidia Hpc Sdk, and we are pleased to have with us Tim Costa from Nvidia. He has been HPC software product manager at Nvidia and responsible for Nvidia Hpc Sdk and compilers and math libraries, in addition to programming models strategy. Prior to joining Nvidia, Tim worked as a performance library architect and HPC application engineer and own enabling efforts for CFD application at Intel. He has obtained his PhD in mathematics from Oregon State University on the development and analysis of numerical methods for fluid flow in stochastic or evolving porous media. So thank you, Tim. Please go ahead, take it away.
All right, great. Yeah, so I'll talk about the HPC SDK here today. There's a few different sections related to programming models, and then the compilers which implement them, and then the various libraries which are important in here too. We'll try to make it seamless as we go through. But I do want to motivate things a little bit before I introduce the HPC SDK, because it's a product we released for the first time this year, back in August. I think it was July or August. And that's still a pretty new product. So for new products, I do want to make sure everyone knows why we made it. And so the first part is to answer just a question that it feels like a simple question, but it's ultimately it's become complex. And that is, how do you program an accelerated system? Now I'm moving forward into the future. But before I do that, I do want to look back a little bit at the past. I think that really helps to see where we've come from to help understand where we are now and where we're going in the future, and so how developers should think about the future in particular of programming accelerated systems. So, if we take that historical view and look at things, back in 2007, before 2007, people were developing for accelerated systems for GPUs for scientific computing applications, but it was really hard, right? You had to map, graphics and shader APIs to scientific algorithms, and so it was a very small, very niche community, and developer velocity was really, really low. And I will mention developer velocity many times today, and to some degree, that's one of my biggest focuses. We talk a lot about runtime performance at NVIDIA. It's really, really important, but it's one of two parts of what actually gets you your quantity of interest, which is faster time to science. If you have to spend more time developing, that's also going to reduce ultimately the time it takes to get you to science. And so we want to increase that developer velocity in addition to the runtime performance. So in that mindset, CUDA really, when it releases in 2007, is an explosion in developer velocity and accessibility of the accelerated platform. Right? It provides an abstract programming model for the accelerated system, which better maps to scientific algorithms. Now, but we know we weren't done back then. I mean, everyone in HPC and supercomputing, and certainly everyone on this call who would be listening to me right now, is familiar with the three Ps, and two of those Ps being productivity and portability. And in my mind, portability is really a specific case of productivity, but it's a really important one. So we knew we weren't done, and so in the early 2010s, worked with the community to develop directed-based approaches for targeting accelerated systems. And of course, that was OpenACC, and which has had a tremendous record over the past 7 or 8 years with applications using it to get to the accelerated platform while remaining performance portable, and even for compilers to be able to ignore the directives if they don't understand them. So, but that leads us to today. All along the way, we've kind of known, what's the shining light on the hill here? The shining light on the hill is, just write in standard languages and have compiler toolchains target the accelerated platform for you, be that a multi-core CPU or a GPU accelerated system. And then from there, of course, you can always optimize, right? And this is sort of the classical way of doing HPC development, even on CPU-only systems. I personally worked on OpenFOAM. That was the heaviest part of my lift when I was in my previous life. And if I asked anyone, is what's the programming model for OpenFOAM? I think most people would say it's a C++ application. Of course, if you look at the kernels, you're going to find x86 instructions, right? So this is a very familiar model for HPC developers. We program in a standard language, and we optimize where we need to with something which has more capability to directly target the hardware. And so now that we've done the right to left description of the history, we're ready to make that claim now today, which is today you start with GPU accelerated C++. You start with GPU accelerated Fortran, and from there you incrementally optimize while remaining performance portable with directives, or go all the way over to maximizing your GPU performance with CUDA C++ or Fortran. Now, of course, I don't know if everyone here watches all the GTC keynotes, but earlier this year when Jensen noted that the data center is now the unit of compute in one of his keynotes, and I actually think this is not a new statement for the HPC and supercomputing world. One of my favorite definitions for HPC is scaling with discipline. Well, what are you scaling up? You're scaling from having a single compute resource like a GPU to a node that has many GPUs as well as a CPU with different architectures connected by one level of interconnect. And then, of course, that sits within a system that is connected by another level of interconnect. And an HPC developer who is concerned with performance needs to be managing all of these different parts of the system explicitly. And so what is the product that NVIDIA provides now to support all those various programming models and issues from developing on a supercomputer? That is the NVIDIA Hpc Sdk. So it's available totally for free. There's no cost using the Hpc Sdk or any of its components. It's available on developer.nvidia.com/Hpc Sdk. It's available on NGC as a container if that's your preferred way to do development. And as well as in the cloud on AWS, GCP, and Azure. It supports all the programming models, which I mentioned on the previous 2 slides ago. So from automatic GPU acceleration of standard C++ and Fortran to OpenACC and OpenMP for both multi-core as well as GPU acceleration, to, of course, CUDA, C++, and Fortran for getting that optimal platform-specialized performance. That's all supported by a suite of compilers. MVCC, of course, is the CUDA C++ compiler you already know and love, but now we have 3 new compilers in the Hpc Sdk with MVC, MVC++, and MV Fortran. You can probably guess those are C, C++, and Fortran compilers, respectively. I didn't really talk about it 2 slides ago, but you probably noticed along the bottom of the slide there was a line that just said GPU accelerated libraries. Of course, if a library API exists for your use case, you should use the API. That's going to give you that platform specialized performance in a way that is just drop-in, easy to use. And so we have a large suite of libraries in the Hpc Sdk, both from core libraries with for sort of your core algorithms like libq++, thrust, and cub, as well as a full suite of math libraries. I'm assuming things like BLAS with any couple of letters before it needs no introduction here, but we also have some new libraries which are sort of blazing trail from NVIDIA, like cuTensor, which supports tensor contractions and element-wise APIs, and we'll see some of its benefit later in the deck, not only as a standalone library, but also as the backend for some of the things we're accelerating in Fortran in ISO Fortran. On the previous slide, clearly, I noted that we have to program the network, and so for that we have a suite of communication libraries from OpenMPI to MVHMM and Nickel. I'll talk about what MVHMM and Nickel are a little bit later if you haven't heard of them. I feel confident you've heard of OpenMPI. And then HPC being an iterative process, we have profilers with Nsight Systems and Compute, and then debugger with CUDA GDB. We release every odd month of the year, and then we leave room for 1 or 2 extra releases per year. So that's a total of 7 to 8 releases a year. And again, it's freely available. So there's no amount of money you can try to give me for this software. I won't take it. All right, let's start diving in a little bit. So I'm going to start by talking about programming in ISO C++ and ISO Fortran and getting on the accelerated platform. And beginning with C++. So if we look at some of the examples I'm going to show here where we're accelerating C++, they're going to be using the C++ parallel algorithm. So I do want to just briefly introduce what they are. They're introduced in C++ 17. Their major feature is the use of parallel and vector concurrency via execution policies. So the idea here, and you can see it highlighted in green in the top box, is that you take your favorite algorithm from the C++ standard library and you add a new first parameter that's an execution policy. And if you choose par or par unseek, and you're using NVC++, that is going to automatically leverage the GPU for you with CUDA unified memory underneath the hood. It does introduce several new algorithms as well, so let's take a look at a use case here. I'm going to start with the Lulash Hydrodynamics mini app. This is out of Lawrence Livermore. It's about 9,000 lines of C++. Parallel versions, if you go look at the GitHub repository, are available in MPI, OpenMP, OpenACC, CUDA, Raja, Cocos, and now ISO-C++, because we went ahead and upstreamed that. And it's designed to stress compiler vectorization, parallel overheads, and on-node parallelism. I'm definitely going to show you performance, but like I said, I want to talk about developer velocity as much as anything else. So let's first take a look at part of the code. So this is one of the functions from Lulash, calc hydro constraint for elms, and on the left is an implementation that is what I think of as the traditional way of programming, parallel programming. You take a serial language like C++ and you pair it with a parallel programming model. So in this case, OpenMP. But we could make the same slide with OpenACC if we wanted to, certainly. On the right is what it looks like when we use a single parallel language. So we've replaced the combination of a language and a programming model with a single parallel language. And you can see that it's composable, it's compact, and it's elegant. It's easy to read and maintain if you're a C++ developer. And it's fully ISO standard. And the reason that I really lean into that ISO standard statement is there's really no greater guarantee of portability. You can compile this today with G++, with ICPC, or the Intel compiler. I know they have another one now, IC with an X in it, and I presume that will also work. The Microsoft Visual Studio compiler, and you can run it on all the cores of your Windows laptop, if that's what you want to do. If you use MVC++ and you have an A100 at hand, though, this is the performance you get from Lulash with the exact same ISO C++ code. So on the left, what we're doing here is we're normalizing the performance against running on all 40 cores of a dual socket Xeon Gold 6148. And then you get 7x performance for free in terms of developer investment. So that's, when your developer time is 0, your developer velocity is pretty darn high. And again, with that same ISO C++ code. I do also compare here to OpenACC. The way that developers have been programming accelerated systems for half a decade now in a performance portable way has been with OpenACC. So if we're going to talk about a new method, which we think is the future, we do need to compare it to the existing methodology. And so you can see here in this case, we're actually keeping up with OpenACC. And if I put number bars up here, you'd actually get there's a slightly higher number in the C++ case. Now, results are going to vary depending on your application workload, and there are things you can do with OpenACC, in particular with respect to memory movement, that are not going to be possible in C++, which leverages unified memory. So that's why we, in that first slide, we talk about incremental optimization with directives if needed. In this particular case, for this app, it's not needed, as we can see here. Moving past what Nvidia has done themselves with ISO C++, accelerated ISO C++, we look at this STLBM code. It came from Professor Jonas Lott at the University of Geneva, who is a leader in lattice Boltzmann codes. And he implemented a framework for parallel lattice Boltzmann on multiple platforms, including many-core CPUs and GPUs. And he implemented it entirely for the parallel parts with C++ 17 parallel algorithms. That means there are no language extensions, there are no external libraries, there are no vendor-specific code annotations or pre-compilation steps, and we are looking at almost 13x better performance geomean over the collision models in STLBM from just adding an A100 over all 40 cores of a Xeon Gold 6148. Again, it's the exact same ISO C++ code. One of the other interesting results we've had recently, as Python becomes an increasingly important presence in HPC and supercomputing, is, it occurred to actually someone on the Rapids team that, one of the ways you've historically gotten C++ levels of performance in Python has been using Python. And now we have MVC++, which is giving you GPU performance in C++. So why don't we chain those two things together to Python? to writing what looks like, looks and feels like standard Python. So you can see here that that's what we're doing in the performance chart on the right, and it's for a Jacobi solver. We chose a Jacobi solver because it's easy to write on a slide. People kind of know exactly what it does and what it means, but it's also not toy code. I mean, those who work in fluids around here know that in your multi-grid solver, you're going to have a smoother a smoother that you're using, which is going to occupy massive amounts of your wall time. And Jacobi is one of those possible smoothers. So it's something that will actually show up in people's workloads. And in terms of performance, this time we're normalized against NumPy. NumPy, of course, is single-threaded. We also do want to show that this works for multi-core systems. So the blue line is showing the speed up over NumPy using NVC++ with Cython on a multi-core CPU system. And then the green bar is adding an A100 in here as well. Again, no code changes there between the CPU and the GPU. So everything I've talked about so far has been from the top left of this slide here. All of the actual code that is being automatically accelerated is C++ 17 parallel algorithms. I do want to note that C++ 17 had two other major advances with respect to parallel and accelerated computing, which aren't user-facing, but they're really important as they lay the groundwork for long-term development in this area, and that's forward progress guarantees and memory model clarifications, which extend the C++ execution and memory model respectively for accelerators. C++ 20 then came out with a scalable synchronization library that is available now in libq++. That is a library in the Hpc Sdk. And then in C++ 23, of course, I can't stamp any of these as in C++ 23. Those decisions have not been made yet, and I don't make them unilaterally by any means. It's a committee that we work with to try to define what's in the standard. But I can tell you that these things will all come to NVC++, our compiler, as preview features this year in 2021. These features are really, really exciting for accelerated computing. So executors, and I'll talk a little bit about executors and linear algebra on some slides that are coming next. But just to really quickly say, executors sort of standardize kernel launch and greatly enhance the flexibility of programming in ISO C++ on an accelerator and on a multi-core CPU. We also have stood MDSpan and MDArray. These are multi-dimensional array abstractions. It's one of the kind of funny areas where we get to say Fortran is ahead of C++, and in that it already has HPC-oriented multi-dimensional array abstractions, while C++ doesn't, but that will be addressed with stood MDSpan and MDArray. Linear algebra, we'll have another slide in a minute, so I'll just skip over it for the second. But we're also working on extended floating point types. So you've probably noticed that various different hardwares are introducing new data types, new compute types in some cases, like the TensorFloat 32, that obviously are not part of the C++ standard. And so the purpose of this proposal is to put in place a framework for compilers to support in a standard way data types which are not even known at this time, right? It's an extensible framework for data types in C++. So that'll be really important for accelerators as well. Okay, let's talk a little bit about executors and linear algebra because they'll come this year, and I think they're really important for accelerated and parallel computing in C++. So on the left is a look at something I think we're all familiar with, a call to dgmb from the BLA specification. And depending on how long you've been doing HPC development, you may or may not still remember what I assume was your initial disgust over that API if you're a C++ developer, right? I still have gotten the question when I've gone back to my where I got my PhD, and I give talks about things, and I talk about linear algebra, and I show a BLAS API, and people who haven't thought about that yet say, why are there 11 arguments to that? So it's a very unfamiliar and uncomfortable way to do linear algebra in C++. But there are some actual functional limitations to it as well, right? The scalar types are in the function name. This makes it very hard to do extensions in terms of mixed precision support or new precision support. And the Fortran data layout has complications. You have to either deal with it in your application, or you have to do transpose tricks with how you call the BLAS API. So all of this will get addressed with the C++ linear algebra proposal that's in flight right now. You can see that the call to matrix vector product has 3 arguments, the expected ones. You want to multiply AX and B, and you put AX and B as arguments into the API. The function name does not encode the scalar type. So the same API can very flexibly handle and naturally handle mixed precision, which is increasingly important not only in other application areas like AI, but also in HPC. It includes the equivalent of every BLAS function. And then in terms of specific features for accelerated computing, we'll map this in the back end of our toolchain to our vendor-optimized libraries, cuBLAS, which means not only do you get GPU acceleration, but you get tensor core access in ISO C++. Another really exciting development that's being worked on is Executors. So Executors, I've heard them described as allocators for threads, but they simplify work across CPUs and accelerators by being a uniform abstraction between the code and the diverse resources. Again, this would be ISO standard, right? And that the point of continuously hammering on that, again, is that there's really no stronger guarantee of portability than being the ISO standard. It standardizes kernel launch, you write once, you run everywhere, and this really adds flexibility. The C++ 17 parallel algorithms, while because of how C++ works with lambdas, it has a good amount of flexibility despite being library APIs, they are still library APIs. And so executors by standardizing kernel launch will give us a lot more flexibility in terms of writing accelerated ISO standard C++. Okay, let's talk a little about Fortran. So, our mission, our goals, our plans, what we're doing to enable Fortran is no different than C++. We're heavily engaged in the Fortran committee, and we think that ISO standard Fortran is also the future for doing HPC development in a Fortran app. We have a number of features which are accelerated today automatically. I'm going to talk about them now. This first one is one of my favorites. One of my previous lives was as a BLAS developer, and I think the first time you sit down as a BLAS developer, you get given something that looks a lot like this code on the left. For me, it was C, not Fortran, but the same principles. And you're sent off to a corner and say, take this triply nested loop and come back when it's 90% efficient on whatever core you're targeting. And it's a lot of work to do that, right? You start blocking and unrolling, and then you introduce explicit vectorization, and you realize you're not going to be able to get there from a standard language, so you have to start writing, adding x86 intrinsics. For me, I was working on x86. Start using some specialized code in the middle. And by the end of the day, instead of having 3 loops of a standard language, you've got some number of hundreds of lines of assembly, but you got some great performance. And what I love about this slide is it's the complete opposite story, right? We go from the left with naive code, triply nested loop, to the right, where we are calling part of the ISO Fortran language with its intrinsic matmul. And what we get is the performance on the right. So this is, it's kind of hard to even tell where the bar is in terms of teraflops for the naive inline code on V100. And then calling this much simpler code on the right, we see that on a V100, we're at about 7.1 or 2 teraflops of performance. And I'm sure we've all memorized our speeds and feeds for all the Nvidia GPUs, but the peak there was about 7.5, so very close to the peak here from a call to something in the language. And then on the A100, we are well over 17 teraflops performance. Again, I'm sure you already know, but the peak there is 19.5. Just as important and interesting on the peak from A100, though, is getting to above 9.5 teraflops performance requires that you're using the double precision tensor core. So we are, while tensor core access in ISO C++ is aspirational, and we'll have it once we implement the linear algebra proposal in our compilers this year, we actually have today access to tensor cores in ISO Fortran. Now, I can imagine being in the audience and saying, well, that's a matmul. I mean, that's pretty limiting, right? But it's much, much broader than that. So the array intrinsics in Fortran are much broader than matmul. It's just a fun one to show off because you can see the leveraging of the tensor core. This is not an exhaustive list.
Sorry, we have multiple questions. I want to get through them before we continue.
Okay.
Yeah, so So I think the first one is, with embracing ISO C++, will CUDA go away?
No. So we the way to think about this is the same way that I described the open phone application at the beginning of the slide, right? You program in ISO C++, and it's accelerated on the GPU. If you have a part of the code which is a really critical kernel, it's your bottleneck, and specializing for the target will enhance your performance, that's what CUDA is there for, right? CUDA is your platform specialized explicit GPU programming model. And so you can leverage CUDA to get the best of the platform where it's needed in the application. But overall, your code is accelerated because you wrote it in ISO standard C++. So CUDA is never going to go away. But CUDA is how you leverage the best of the platform for runtime performance, while the rest of the code is automatically accelerated because you're writing in the standard language.
Thank you. So the next question is, will there still be a compile for GPU then link for CPU?
Sorry, I couldn't understand.
So the question Frank is asked, like, so are we supposed to compile for GPU and then link for CPU?
So we're not all the way there yet today on the on this for stdpar, but ultimately what we're going to do with the compiler is produce fat binaries which run on CPU and on GPU. So you can compile once. If you're writing in one of the standard languages, and you can compile once, and then that code will run on your multi-core CPU, and it will run on your GPU. So it should be a very seamless process. Now today, with C++ 17 parallel algorithms, there are some additional steps required to target the CPU, but that is a 2021 roadmap item to clean that up. But while the GPU support right now is very, very nice and smooth.
Yeah. Okay, thank you. So I see a lot of discussions about the machines that they use different NVIDIA architecture, and I feel like we've already their answers. The next question is about, can this SDK be used for development of CPU code on a machine that does not have any GPU or any system with a non-NVIDIA GPU?
So we don't have any support for a non-NVIDIA GPU, but absolutely it can be used for development on a CPU-only system. And on a system that has a non-NVIDIA GPU, it's just we won't leverage it, right? So the compilers in here, MVC, MVC++, and MV Fortran, they support ARM server CPUs, they support Power CPUs, they support x86, both Intel and AMD CPUs. And by support, I don't just mean as a host for a GPU. I mean in terms of providing high performance vectorized multi-core code with the programming models that I've discussed for those multi-core CPUs.
And I think the last question is, how does it compare with Matmul on Intel MKL?
So how does this on this last slide here compare to Matmul on Intel MKL?
I don't know, Alessandro, do you want to clarify, what was your question?
I think it's CPU to CPU is the question they're asking, if I follow this thread, Tim.
I see. I actually haven't measured this on a CPU, so
yeah, I don't think we've measured it either. This is Tom Gibbs speaking. Yeah, from the perf lab, I don't think we've measured CPU to CPU performance on the software.
All right,
okay.
So I'll keep going. Welcome.
Actually, one more question came
Sure.
up. Sorry.
Sure.
Does the C++ compiler and library provide ABI compatibility between user codes compiled for different C++ standards in the fashion that G++ does, for example?
I'm 99% sure that the answer to that is yes. There's probably nuance, and I didn't bring the right technical bodyguard with me to back up that answer. So if let's follow up offline. Let me double check with the right people and follow up offline.
Okay, thank you. And I guess there are more questions coming. So I'm going to take 2 more questions and then we continue and then we can ask more. So can someone with knowledgeable outline the difference between OpenACC and these compilers?
Do you want to? the difference between OpenACC and so I am going to talk about OpenACC a little bit after I'm finished with Fortran. So maybe we should see whether that section addresses the question.
Yeah.
And yeah, okay. Okay, so right. So what I was saying here was that MapMul is a nice example because it lights up the tensor core, and I think everyone knows what it looks like to write a naive MapMul and then to call something from the Fortran intrinsic. But there's a wide range of intrinsics in ISO Fortran that we accelerate the same way, and the reason for that is that we're using that cuTensor library as the backend, and it's a very flexible library. So it's able to support any combination of things which look and feel like a tensor contraction, which is an abstraction of matrix multiplications to higher dimensions, and anything that looks and feels like a permutation of a tensor. So that gives us things like reshapes and conjugates here and spread, as well as your matmuls. And so any combination of those that NV Fortran encounters, it'll map in the backend to cuTensor and give you that automatic GPU acceleration as well. So very, very flexible. One of the more recent additions to programming in Fortran on the GPU was our addition of automatic GPU acceleration to do concurrent. So if you're not familiar, do concurrent is it's a parallel loop in ISO Fortran. It can support multiple iteration dimensions, which gives the compiler some opportunities for optimization. Again, I'm showing you a Jacobi smoother for the same reason as discussed before. And you can see here that, again, the exact same ISO Fortran code, no code changes, so 0 developer time, which is infinite developer velocity. We get 13x better performance by just adding an A100 to the system here. Again, with a comparison to OpenACC, this time if I put the numbers up there, the OpenACC number is slightly higher, but you can see that we are within touching distance of the OpenACC performance. So right where we want to be for that acceleration of Fortran. Taking a look at sort of the Fortran roadmap a little bit. Again, I'd like to add this extra box on top. We don't know exactly what year we're going to see the next Fortran specification. We do know that it has a really important feature for accelerated computing, in that do concurrent is getting a reduction subclause. But we do know that we're going to add that to our compiler this year in 2021. So again, we'll mark it in some way as a preview feature because before we make it official, we want to make sure we have all the spellings exactly as it'll show up in the Fortran standard, but it'll be usable by our developers this year in 2021. All right, let's talk a little bit about directives. So I mentioned earlier today, that OpenACC has been the vehicle for directive support for accelerated systems for a number of years now. So I'm going to start by talking a little bit about OpenACC. I don't know how familiar anybody is, so I apologize for the 101 if it's too high level, and then I'll move on from it very quickly, I promise. But the idea here is, OpenACC directives are incremental, single source, interoperable. They are performance portable. They support, in our compiler toolchain, CPU, GPU, in addition to many core support on that CPU. And you can see sort of 3 different key concepts here with managing data movement, which is actually how I showed OpenACC's relevance in the very first slide. If you think about programming in ISO C++ or in ISO Fortran, and noticing that there's a performance problem related to memory movement, one of the ways you can remain performance portable and take explicit control over your memory is to interoperably drop in some OpenACC directives to control where your data is while still programming primarily in the standard C++ or Fortran. And then we have initiating the parallel execution as well as optimizing loop mappings here. So I think it's a very easy to understand model for doing accelerated computing with directives. Well, this really kind of repeats what I said before in terms of it being performance portable, but a little bit more visually, that we will, with NV Fortran here, target both the multi-core with an ACC multi-core flag, as well as GPU with -ACC equals GPU. One of the features that I think is really interesting in OpenACC, which is not available anywhere else, as far as I'm aware, in any other programming model, is the ability to compare results between CPU and GPU. This OpenACC auto compare. And we can see here kind of a visual representation of how a normal OpenACC execution mode would work with no auto compare, right? You're running something on a CPU, you copy data into the GPU does some execution, and then you copy data back out, and you're working on the CPU again. So just normal way of executing how you would do at runtime. Now during development, though, especially if you're a first-time GPU user, you might want to verify, or if you're debugging something, Harry, you might want to verify, that your results are correct, or find where something went wrong in terms of results being incorrect. And what autocompare allows you to do is to run the same region redundantly on CPU and GPU and get the results compared out the other end. So this feature is really, really well received by the OpenACC community. So it's one that anytime I talk about OpenACC, I want to make sure and point out, because in particular for new developers on GPUs, this is really, really useful. And sort of the final thing to say about OpenACC that I also want to say is it's widely successful, widely adopted, proven model, right? I'm not going to try to read all the quotes. One of the problems with having this many adopted applications is you can't actually read anything on a slide when you put them all together. But you can see a number of applications here, which I'm sure are familiar to you. Gaussian and VASP, it'd be hard not to know what those are, I think, working in the HPC space. And these are, OpenACC accelerated applications today that are doing great work, great science. Now, OpenMP is the new kid on the block for GPU accelerated directives programming. We did just release our open beta support in the Hpc Sdk. That was in our 20.11 release. I think that it shouldn't be a surprise to Argonne users. This was that we're implementing a subset of the OpenMP 5.0 specification. It was determined by application priorities and as well as what we think will be performant and portable and productive for our application users and our compiler users. The details about the subset are now available in the product documentation. So that wasn't true until 20.11 when we went into open beta. So you're welcome to go take a look there and see which features have been implemented and are available. And it is interoperable. I call out CUDA streams here, but it's interoperable in other ways too, in the sense that you can interoperate with OpenACC, you can interoperate with ISO standard languages, automatically accelerated, as well as with CUDA. That's a key part of our programming model story, our strategy, our efforts, is to make sure that all the various programming models are fully interoperable. All right, so for the bottom bar, which I referenced before when we were looking at the Hpc Sdk, it's really the first place a developer should go to, which begs the question, why is it the last section in my deck? But be that as it may, let's talk about some libraries here. I want to start with the math libraries. So we have a rich set of math libraries, and they really expose in a seamless way to the developer all the greatness of our architectures as they come out. All right, so looking at some of the A100 features here across them, we've got support for all the new tensor core precisions in cuBLAS and cuTensor, actually as well as in cuSolver, which is pretty interesting. Not just the FP64 tensor core, but we have some iterative refinement-based solvers in cuSolver, which leverage the lower precision internally as a black box and just gives you better performance with an FP64 result. And then the sparse MMA tensor core is a newly enabled feature of cuSparse. We released the cuSparse LT, which is a library extension to cuSparse at the end of 2020 to enable direct access to the sparse MMA tensor core. And then for your more memory bandwidth bound type routines, most of cuSparse is memory bandwidth bound. All of cuFFT is memory bandwidth bound. And then parts of cuBLAS, cuTensor, and cuSolver as well, but I just don't want to call everything out and have too many words on the slide. We leverage the increased shared memory and L2 cache sizes and get much better performance that way, as well as the improved memory bandwidth in those libraries. A few more specific things I want to call out. Of course, if I want to talk about libraries on tensor core architectures, I got to show just a mean green performance slide that shows you how close to peak we are with with gems. And so that's what I'm showing you here. You can see we're up in the 19 teraflops plus regime for gem and cuBLAS, double precision gem and cuBLAS, which is 2.4x of V100 when the peak gain is 2.5, so right where we should be. But I don't think that's the most interesting thing which happened in the latest releases of cuBLAS. So two other things happened that I think are really impactful from the developer velocity perspective. One is the tensor core acceleration is now automatic. If you were to look at older versions of cuBLAS, you had to ask for tensor core acceleration, even if the precisions in your call were appropriate for tensor core acceleration. Now, if your precisions are appropriate for a tensor core, we will automatically leverage the tensor core. You don't have to ask for that. Tensor core acceleration. So it used to be the case that even if your precisions were correct and you asked for tensor core and you didn't meet a set of size and alignment requirements, you did not get tensor core acceleration. Now the reason for that was not just being prickly or sticklers to something. You get the best performance from what used to be the requirements. But that still left a lot of performance on the table, in particular for applications where it was hard for the developer to get to the place that the matrices were being multiplied and actually do things like padding, right, and realigning. So for those particular cases, as much as we would like people to get things into the optimal configuration, they couldn't, and so we were leaving performance on the table. And so now we can see the difference here. I'm showing it all in V100 so we can do apples to apples. But Align 1 and Align 2 did not meet the requirements of the old cuBLAS, and so you can see that their performance is on the bottom line of this chart. Well, Align 8 does meet those requirements, and you can see that it's doing very nicely with peaking up at around 122 or 3 teraflops of performance for FP16. The green lines are the newer cuBLAS releases. So now you can see that with Align 1, we've got a roughly 3x performance improvement. So not the peak of what we can do, but a significant gain if you're not able to realign, and pad your matrices for tensor core. And then Align 2 gets 5x, and then of course if you have, if you're able to get to the optimal configuration, which is now a performance recommendation instead of requirement, you get that peak performance of up above 120 teraflops. cuTensor I mentioned earlier. I just want to show a little bit of performance here. So it supports element-wise operations, mixed precision support. It's a very nice flexible API, as well as element-wise fusion. So the element-wise API in particular is very flexible. You can do multiple different element-wise operations, and it will do fusion inside the library. It also has that automatic tensor core acceleration, and we had some tremendous performance gains by implementing some new algorithms when we released for A100. So we're seeing a up to 13.1x speed up. Obviously, the peak speed up from the actual hardware is not that high, but we were able to do some new things with the algorithms and get even more. And then average about 3.4x speed up over our test cases. I think it's important sometimes to look a little bit up the stack even within the libraries. So I can show off cuBLAS performance till the cows come home, but it's a gem. Tensor Core is a gem, so I ought to show it in something one layer up the stack to see that the benefit translates. So here is an LU solver in FP64, and you can see we are about 2.3x faster on an A100 over a V100. Remember that if you use the tensor core, your peak gain is about 2.5. So we're able to get that benefit of the tensor core through up the stack into the LU solver, even though it's not exclusively a matrix multiplication. So that's a very nice result here, with up to 2.8x speed up actually on these cases. Many problems in HPC are sparse. That sort of classical sparse pattern where you're 98% sparse and irregular. And so we've done a lot of work in our cuSparse library to better address those use cases over the last few years. One of the major pushes has been to move to generic APIs along the way, looking at performance and finding new opportunities. Our most recent release of a new API is SPGEM. So this is our sparse matrix multiplication. In addition to modernizing the API, we also got about 4.6x geomean speed up over the legacy APIs on V100 to V100. And then you can see the speed ups from A100 here on the right of this. And I am getting a little limited on time, so I'm going to just kind of cruise. cuSparse LT is, again, I mentioned before, is an extension to using the sparse and MMA tensor core. This is available standalone on developer.nvidia.com, and really encourage people to look at it. It's in a kind of what we think of as an open beta. And we are iterating on this design, and so we want to definitely engage with any developers and talk about how we can enhance it for getting better matching application needs for leveraging that sparse and MMA tensor core. This will be a nice segue into the next section, which is about communication libraries, but we do have multi-GPU support in the libraries. We've had multi-GPU support for a single process in FFT for a very long time, since long before I was at NVIDIA. But we're working now on multi-node, multi-GPU FFT, which will be coming out relatively soon. In cuSolver, over the past 1.5 to 2 years, we've added multi-GPU eigensolver, LU, and Cholesky, and we'll be moving into the multi-node, multi-GPU area here soon there as well, starting with an LU, but with more features to come after that. And of course, cuBLAS has had multi-GPU support for quite some time, but we've got significantly enhanced performance in a library called cuBLAS MG, which is currently in early access, and we're looking for engagement on that one as well. I apologize for my dogs, but this is the nature of doing presentations these days. So talking a little bit about communication libraries, which I'll have to really speed through. We have 3 in the Hpc Sdk. We've got, of course, built, tested, integrated OpenMPI. MPI is so fundamental in HPC, but also 2 of our own NVIDIA libraries with NVSHMEM and with Nickel. And I want to talk a little bit about those here. If you haven't heard of NVSHMEM yet, I think it's something you want to go look at. So this is a GPU-optimized SHMEM. Not familiar with SHMEM. SHMEM is a PGAS model, so partition global address space. It has, a number of advantages, but one of those is along that, developer velocity idea that I've brought up many times here, in the sense that its intent is to be, as easy to use as shared memory programming, but with the performance characteristics of a distributed model like MPI. And one of the pre-release engagements that we had in this area with Cocos on CGSolve, that's really where it shined. We didn't actually see a performance benefit on that, and I'll just be upfront about that. But that had tremendous number of lines of code reduction from the MPI version to the NVSHMEM version, which means lower development costs, lower maintenance costs, all those great things, which ultimately lead to faster time to science. Now, the NVIDIA library performance matters too, and with our other pre-release engagements, we did have very nice performance results. One of them I'll show you here. So this is the impact of NVSHMEM in CUDA. That's CUDA with a Q, quantum chromodynamics on CUDA. And on a single node here, we saw up to 1.7x speed up going from an MPI-based implementation to a NVSHMEM-based implementation. And then on a multi-node configuration, up to 1,024 GPUs, we had 1.4x speed up for that same problem. So not 10 or 20x, but for communications libraries, which are really, we can think of as force multipliers for the performance we get from the compute resources, really a tremendous result here, in addition to the increased developer velocity from the programming model itself. Nickel, and this should be about the last thing that I have to say, I think. So if you're not familiar, this is a library which implements collectives optimized for NVIDIA GPUs. One of its really primary features which give its benefit is automatic topology detection. There's many different algorithms you can use for collective operations, but if you can detect the topology, you have a good idea of which algorithm to choose to get the best performance possible, and it's something Nickel does very well. Nickel 2.8 had some new enhancements, including scaling up the number of systems that we're able to demonstrate performance on, up to 24,000 GPUs, which is a big system. Improved all reduced performance on Ampere GPUs, support send receive operations to cover all communication needs, and improved all-to-all performance and usability. Now, Nickel has historically been thought of as kind of a deep learning library, but it's starting to see some adoption even in just classical HPC simulation type applications. And one of those is VASP, which I think everyone is very familiar with. So these are the results using Nickel in VASP, Nickel 2.8 in VASP, and you can see that you're up to depending on the use case here, or the problem, we're up to 1.54x faster by leveraging nickel over the MPI version. So that's, again, really big gain from the communication library, which is a force multiplier for the rest of the compute happening on the platform. Okay, I'm 99% sure this is the last slide. And that is, I quickly do want to say one of the things we go for with the HPC SDK is that drop-in ease of use. That we package things up, we test it all together, we integrate components together, and because we know that developing on an HPC system has many different aspects, from having language support in your compilers, parallel programming models, if you're pairing another parallel programming model on top of your language, to how you communicate across the network. And so we're showing an example here with Cloverleaf of drop in the HPC SDK using NB Fortran for the language and the parallel programming model with the open MPI that's built in there, and you get perfect scaling on 4 A100s on a DGX A100, and then 7.5x. It's very good, strong scaling up to 8 GPUs as well. Okay, and I just like to always end on this slide so people see the HPC SDK while I take any additional questions.
Thank you, Tim. That was very interesting talk. So I see one question that I think has already been answered, that it was asked, like, where do we can actually run these SDK, the Nvidia SDK, on any platform, A100, B100, and I think the answer was like, yes, you can run anywhere.
Yes.
So another question coming up is HPC SDK shared memory model.
So there are, it depends. I guess we have to dig a little bit on the question. OpenMPI obviously is not a shared memory model for distributed compute, right? It's a distributed memory model. NVSHMEM does implement something which is a shared memory model across distributed GPUs. So you can program in a shared memory model in a distributed setting with NVSHMEM. I don't think the question applies to the whole HPC SDK, right? We support multiple different parallel programming models for distributed computing, and one of those is a shared memory model, and one of those is a bulk synchronous distributed model with MPI.
Thank you. So the other question is related to how do you get these on ThetaGPU? I think we are working to make that in centralized format. It's not yet there, but I think each person individually can install that on ThetaGPU. Is that correct?
Yeah, and anyone who is aware of the HPC SDK can go download it, take it to the system they want to run on, and use it. We are working through licensing issues to get it, centrally installed on Theta. I'm expecting that won't be too much longer, but there's nothing to stop a developer from grabbing the HPC SDK themselves.
So the other question is, did the results you showed earlier, and you can also look at them in the chat, with the SCD PAR for a single GPU, right? Is there any support for multi-GPUs with current solution?
Yeah, that's a roadmap item. Today, we don't support multiple GPUs, but it's a near-term roadmap item to add that support, and people are working on it. And I want to be clear, I mean single process multi-GPU. So, like on a DGX A100 where you have either 4 or 8 GPUs, and you call a C++17 parallel algorithm with a parallel execution policy, then we would target the 4 or 8 GPUs for you. So that's what we're working on.
Okay, thank you. Okay, so there is another question related to the SDK download. I think they put that link already. Is there a spec package for SDK?
Yes.
Okay. Next question is SCD PAR modern execution interoperable with two FFT libraries? With CUDA, we need to do explicit memory movement in order to call distributed CUFFT.
If you're using CUDA for unified memory, which you will be if you're using stdtar, you should not need to make an explicit memory movement to call QFFT. The only reason I'm using a more hesitating voice is I haven't personally done it, but I would expect that to work. And if it doesn't, I need to know about it.
Okay. So we had a lot of questions. I don't know if there are any more questions. No, I want to let you guys know that we will be providing, I will ask him to provide the slides to me, and then I will distribute it to all the people who registered. And then we also will be providing the recording as well. If there are no more questions, I would like to thank Tim and everyone who helped with this presentation. It was very well received, and we had lots of questions. And I'm sure they can email you if they have more questions.
Absolutely.
Yes. Well, thank you, everyone, and I hope you have a good rest of your day.
Thank you.